So welcome again to this next session of this IEEE online forum on climate change. Our next speaker is Alissa Park from UCLA, and she would be sharing her thoughts on creating a new circular carbon economy via carbon capture, utilization, and storage. Very briefly about Alissa. She is Ronald Valerie Sugar Dean of UCLA, Sam Valley School of Engineering, and a professor of chemical and biomolecular engineering at University of California, Los Angeles. Before joining UCLA in 2023, she was the Lenfest Earth Institute Professor of Climate Change at Columbia University, where she also served as the director of the Lenfest Center for Sustainable Energy. Her research focuses on sustainable energy and materials conversion pathways with an emphasis on integrated carbon capture, utilization, and storage technologies. She received a number of professional awards and honors, including the Shell Thomas Barron Award in Fluid Particle Systems and PSRI Lectureship Award and NSF Career Award. There are several others that I can see in the list. She also led key global and national discussions on CCUS, including Mission Innovation Workshop in 2017. She is fellow of ACS, RSC, and American Association for Advancement of Science. Over to you, Alissa.
Thank you for a kind introduction. It's been really wonderful listening on all these discussions. I didn't know electrical engineers are so interested in carbon management, so I think I'm in the right crowd. So today, I'd like to introduce what our field in chemical engineering have been thinking about creating a whole new circular carbon economy for the sustainable future. So hopefully we don't need to discuss that there is a problem of or concern about climate change, and that is linked to carbon dioxide concentration in atmosphere. But at the same time, many of you have been seeing over and over again in media how extreme weather conditions impacts daily lives even today. And in fact, this entire discussion in the United States and around the world started about 30 years ago, or more even. So in chemical engineering, we have always kind of estimated from the benchtop in our lab and the ideas we develop in academia or research centers translate into fully commercialized, scaled up technology. It takes about 20 years. So by the time 2013, we've been getting a lot of questions. We gave your field carbon capture area 20 years already. Why don't we have carbon capture technology installed in power plants and beyond? It's a good question. It's a tough one because many of the environmental control technologies, such as carbon capture, is not really money-making proposition, meaning that not only we need to have technology, we need to have a market, but also policy. So there are a lot of complex issues to getting to deployments. We still have a challenge of carbon capture technology is relatively expensive. So we were concerned by 2013 that rest of the technology industries will say, let's give up on this carbon capture technologies. But instead, the whole field had very interesting discussion that if there's some kind of positive emission like what we have now, positive to zero emission is what you would target. But that was about the time we started talking about deep decarbonization, which means that not only we'll get to zero emission, we need to get to negative emission technologies. So what does it mean by negative emission technologies? Which is basically saying we are committed to go back into history and pick up the CO2 we emitted tens and hundreds years ago. So is it that easy, capturing carbon dioxide out of the thin air, which is the environment? Of course, much harder than capturing carbon from chemical plants or power plants, but that much we are dedicated. So not only the entire field talked about, but our current government, when Biden government came in, they thought that this is a big commitment, not just a short bridge technology. We really need to think about entire future, how we manage carbon throughout our natural and engineered systems. So within Department of Energy in the United States, there's Office of Fossil Energy. And now they changed the name of this office to Office of Fossil Energy and Carbon Management. We thought it was really interesting because it really sends out the statement. This is not a short diet we are talking about for carbon footprint. This is a whole new way of we're going to develop industries and provide resources and energy for all the industries and beyond. Not only they changed the name of the office, there were very interesting investment made by US Department of Energy. Maybe some of you heard about this. It's called Energy Earthshot. I thought it was really cool name because it's similar to moonshot, that no matter what, we're gonna get to the moon. No matter what, we're gonna get to energy earthshot of the ultimate goal. If you can see at the end, my mouse is a net zero economy by 2050. This is different than just saying zero emission or decarbonization of a power sector. We are talking about the entire economy by 2050. Very ambitious goal. So the first one was announced in mid-2021, and this was all about hydrogen. So the target was, can we make $1 per kilogram of hydrogen in 1 decade? This is really ambitious goal, knowing the current price of hydrogen is about $3 to $4 per kilo, depending on which hydrogen you're talking about. But another thing is it's really important which hydrogen we're talking about in this particular target. This is kilogram of hydrogen with carbon free. So this is the big challenge, but this is critical to get to net zero economy by 2050. There were a number of energy earthshots announced over the years, and in late 2021, the energy earthshot related to carbon management was announced. And that target is $100 per ton of CO2 managed from capture all the way to storage or utilization to achieve net zero economy by 2050. And these are very unique because the investment is not in millions, it's in billions, because not only they want to invest in fundamental research and also doing translational research and commercialization, they're even considering how to link everything together to create the infrastructure for these. So let's talk about where we started. So carbon capture technology can be done physically or chemically. Most of my research is in the area of chemical carbon capture. So let me discuss what chemically bound or capturing CO2 from mixture gases. So for example, one of the largest demonstration carbon capture technology process in the United States is in Houston, called Petronova project. It started 2016. It stopped a little bit during the pandemic. We're going to be restarting. I think they already restarted again. And it's capturing more than 1 million tons and millions tons by now. And the way it works is that CO2, carbon dioxide, is acidic gas. In order to bind and capture acidic gas, you need base. So we are using liquid basic solution to capture carbon dioxide. This is the simplest way, the most well-known way of capturing CO2. So if you look at the green reactor on the left side figure, that's the CO2 capture reactor. Usually lower temperature, 40 to 60 degrees C in the power plant, and depending on what flue gas you have in your chemical plant, will take even ambient air or slightly higher temperature CO2 containing stream to grab onto CO2 very effectively and very fast rate. But you're not going to just catch. All the separation technologies are catch and release, catch and release. And during the entire process, we need to continue to recycle the material, capturing CO2, so that we can have many thousands and thousands cycles to achieve economic feasibility of technology. So now green is the catch reactor, Red is the released reactor. So in order to release, catch was the downhill reaction, meaning that you have to put energy in to release the carbon dioxide. The energy can be in form of heat, or it could be pulling vacuum, or both at the same time. So this is the typical CO2 capture technology, which we already scaled up. One of the challenges of this particular technology is that amine is the basic functionality. Amine-based liquid solvent cannot be used as a pure form. You need to dilute it in water. So this solvent system is up to 70 or more % water in the system. And water doesn't have a high solubility of CO2, so the fact that you have water is kind of inert. So looking at the green reactor, let's say 40 to 60 degrees C, that heat we need to provide in the release reactor is 120 to 140 degrees C, which means that you're boiling all that water, cooling it down, boiling all that water and cooling it down very fast. That's one of the things we need to do, carbon capture. So that requires energy. So we were all estimating in order to install carbon capture technology in such a process or chemical plant or power plant, how much more energy do we need? And estimation is you need to, if you do this in a power plant, you will you will reduce the power plant efficiency by 1/3, or in order to produce same amount of electricity, you need to burn 1/3 more fuel. So this was challenging. It does not mean we need to stop this technology. No, this is one of the few technology we already know at this scale. So if we need to build something today, maybe we still have to go to liquid amine solvents. So a lot of us are looking at heat exchangers, better heat management so that we can minimize the parasitic energy consumption for carbon capture. But at the same time, people got excited that, well, if we like the amine functionality, which grabs onto CO2, but then want to get rid of all that water, can we develop new materials, which is water-lean or waterless? So this is a second generation, new type of CO2 capture materials, and this is one of them. This example is a material developed in my research group working with the Lyndon Archer at Cornell University. By tethering polymers onto nanoparticle with the right grafting density and right size and all that so on, we were able to make liquid. Although there's a nanoparticle which is solid, we make liquid-like material as shown in this photo. And this liquid-like material is very interesting because we can create the unique structure of these polymers so that we can create as much free volume as possible in between polymer chains to pack a lot of carbon dioxide in that free volume. One of the things we wanted to see first was after making this material called NOHMs, Nanoparticle Organic Hybrid Materials, we wanted to see, did we change structure of these polymers compared to untethered polymer? Did we create a lot of free volume, which we were trying to do? This is a 2D ROSY NMR data showing that left-hand side and right-hand side, major difference, if you're not familiar, is much less signal on the right-hand side. Basically, what he's saying is that these polymers in NOHM system are stretched out and far away from each other, creating a lot of free volume in between these polymer chains. We also checked whether it's thermally stable because we want to do thousands and thousands temperature cycle to capture CO2 and release that CO2. As you can see on the right-hand side, NOHMs perform really well over 100 cycles, but the PEI, which we started with, degrade almost 80%. So which means that these materials are fantastic, but if we don't improve the thermal stability by making NOHMs, it won't work very well. So it seems to be very positive looking at the NOHMs doing CO2 capture. The only thing now we had to do was just adding as many amine functionalities along the polymer chain, which will be targeting CO2 and binding CO2 effectively. And as you can see in this figure, from bottom to up, each time when we have more amine functionality, CO2 capture capacity per gram of material keep going up. This is expected. So we got really excited. Yes, we can do effectively capture CO2 from mixture gases. But then now you need to think about all these materials should be applied in the huge chemical plant I showed you earlier. So we start thinking about, instead of making tiny amount of material in our lab, Well, now we have to start thinking about scaling up bulk materials, how these gonna be even moved around between reactors and how to create a lot of interfaces between gas and liquid phase so that we can have effective kinetics for CO2 capture. So first thing we checked was viscosity. And if you look here, viscosity of the lowest group, this particular group is a liquid solvent amine-based one, which we use already. It's very similar to water-like consistency, very easy to pump it around, creating different reactor systems is very easy to do. Second group with the red dots are ionic liquid, similar to NOHMs material. These are very high viscosity. And when we checked our ionic liquid, our NOHMs material is even higher. And if students are in the audience, I looked at it first and I was very sad. And when I looked at this figure again, I was really depressed. And there's a reason for it. Hopefully you see that y-axis here is a log plot. So basically, we're orders of magnitude higher viscosity. So why do we care about the viscosity of this material? High viscosity means it's hard to pump. You will not pump at this viscosity. It's like pumping honey throughout your reactor system. Second, high viscosity means it's really hard to create interfaces. So first we were a little bit concerned about this and then, well, a lot concerned and then didn't know what to do about it. But always challenges can be also opportunities. That was about time some of my friends at Lawrence Livermore National Lab, my collaborators, start to encapsulate salty solutions to capture CO2. They were doing the precipitation, dissolution cycles. But I thought those approach was really interesting. So if you have honey like a fluid, like really viscous, what if we can chop them apart and package them so they're all segregated and creating a lot of interfacial area while keeping them as liquid? And that's what we did. So working with the Lawrence Livermore National Lab, the blue color is now our NOHMs material. We just put the dye so that we know exactly where NOHMs is. White colored fluid is UV curable polymer. Now you're making droplet inside a droplet in this microfluidic device. And then second stage, you just need to UV cure the white part, which is UV curable polymer only. And we are hoping to have this microcapsule of a lot of NOHMs material to create not only a benefit, combining benefit of liquid solvents with the benefit of a solid sorbent. So here are some examples of what we actually made. So instead of making nanoscale material, now we are making hundreds micron scale, still very tiny, but because it's hundreds micron, we don't need to worry about the nanoparticle going everywhere and hard to capture them. We can actually design very unique reactors. We can do multi-core and single core, many different designs, as you can see. And this shell material, which is UV cured polymer, is so CO2 can diffuse through very easily while not letting NOHMs outside. So here are the data showing that red series of data is showing that it's very sluggish, very low, slow reaction kinetics when we don't encapsulate our NOHMs. But the black data set is showing that by just simply encapsulating these materials, we were able to really accelerate how fast CO2 is captured by these materials. So now it looks good, right? After capturing all this carbon dioxide, what do you do? What should we do with these materials, capture CO2? Well, after release CO2, if you do care about climate change, we are emitting so much of carbon dioxide, we need to store. And previous speaker also talked about you can store CO2 in a lot of geological formations. There are a lot of pore spaces we can put in. Right-hand side figure shows that this is a very famous Sally Benson at Stanford. She created this kind of scheme showing that what happens to high pressure, about 150 bar of CO2 when we inject underground. It goes through, it becomes a plume first, and then high pressure plume will go into the pores of this rock formation. Usually there is filled with water, not always, a lot of times, and then usually becomes a little droplet of CO2 and then surrounded by water layer. And third stage, this CO2 will start to slowly dissolve in that water layer. And only if there's a mineral which is surrounding it is reactive, now you can start doing mineral trapping, and which a previous speaker also mentioned. It's nice because it's almost making limestone, which nature does. So from carbon dioxide, which is a very stable molecule, you can go downhill one more to make solid carbonates. If you look at this figure on the bottom right, there's something missing on the x-axis, right? Because we didn't know how each stage would take, how long it would take. Would it take a year? Would it take 10 years? Would it take thousands of years? And there are some evidences showing that, for example, Carbfix project in Iceland showed that within 2 years, you can see a little bit of white crystals. The injected carbon dioxide became solid like a limestone. But that's not the only thing we can do. In mid-2020, McKinsey had a really interesting report, I thought. This is the report, their prediction on what would happen on carbon management and what happened to capture carbon by 2030. So that was a 10-year projection, and now we are 2024. We only have 6 years left, we'll see. So light gray bubble is all about their prediction on how much carbon storage will do. I really hope that they underestimate it, because bigger the light gray bubble of carbon storage is better for climate change mitigation. But the part interesting is that black bubble, which is almost a comparable size, and what they estimated or predicted was that by 2030, we'll be making fuel, construction materials, plastics and chemicals using captured carbon dioxide. Very ambitious. Is it going to be economical by 2030? I'm not sure. There's a lot to be done before then. So let's look at this photo of New York City, or chemicals underneath, shampoos or something, detergent you may have used even this morning even. All these have carbon in it. If you look around your room, it'll be very hard for you to find something does not have carbon in it. We've been using the word decarbonization for a long time. We can. So for example, I'm sure this blouse came from petroleum. It's a polymer. But we can decarbonize this blouse by making through biopolymer, maybe. But can we completely decarbonize this blouse? No, because carbon is needed and is a building block, which means that not only we need to do decarbonization for everything you use, everything you see, at the same time, we need to defossilize, which means that the carbon we're going to use for all the chemicals and materials and fuels has to be non-fossil. This is a huge daunting task, and how to do it is a lot of question on how to do it. So let's look at the whole new circular carbon economy we are talking about in our field. So if you look at this blue bubble as a new circular carbon economy, maybe on the left-hand side, which is outside of this bubble, chemicals and materials and fuels, the way we use may not change that fast overnight. It may take a few decades. So we might have similar polymers, similar fuels. And the way we use may not change much, and where it end up in environment or waste streams might be similar. But first, we need to pick that up, and only thing goes into the bubble should be renewable energy. Many of you are working on solar, wind, offshore wind, many other things, and hydrogen, because carbon dioxide has only carbon and oxygen. We need hydrogen as well to build stuff. So we need to understand how to capture CO2 from a wide range of sources, directly from air all the way to waste streams, and how to convert. It could be thermochemically, it could be electrochemically, it could be even biologically, or combination of all. But one thing we have to remember is that this is not a niche technology we are trying to develop. We are trying to change the entire chemical and material industry, which means that from the day one, we need to think about tech to market. And not only tech to market, we need to have economics and policy in place so that by the time as we develop the technology, we have a mean of how to deploy this effectively throughout the entire economy of global economy. One thing I'm not going to have time to talk about is which hydrogen we're going to use. As I alluded earlier to a little bit, that hydrogen we use here has to be carbon-free. So in recent years, we've been talking about hydrogen having different colors. I'm sure many of you know the green hydrogen, right? Because it was to split the water using renewable energy, that's called green hydrogen. They're blue, pink, and even black and gray hydrogen, and the latest color is white and orange. The key is that choose the right color because we need to have minimum or low or zero carbon footprint hydrogen for this whole new circular carbon economy. Otherwise, it's not going to be circular. So let's talk about where are we going to get all this carbon? Because I'm talking about everything you see, everything you use is a huge amount. So maybe we should think about what is the biggest body of stuff. So let's simplistically think about gas, liquid, and solid. What is the biggest body of gas? The entire atmosphere. Biggest body of liquid will be the ocean, and biggest body of solid will be all the mountains and rocks and every solid you see. So the whole climate change is related to CO2 in atmosphere, which is in equilibrium with ocean carbon. So that we have to work on grabbing that CO2 in atmosphere and ocean, but maybe perhaps the solid carbon in rocks, those are the ones maybe we should not use. So is it easy? No, this is one of the difficult way, but because such a low concentration of CO2 in atmosphere. But we've been working on this. We can directly get them engineered way, direct air capture, direct ocean capture are some of these technologies. Or you can go through biological pathways. Terrestrial or marine biomass are the good ways to getting these carbon from the environment, which is non-fossil, and creating a whole new circular carbon economy. So let's talk about direct air capture a little bit. As I mentioned, this is one of the most difficult way of capturing carbon because the concentration is very low. And the technology itself has been developed a little differently. If you remember that CO2 capture unit at Petronova site is huge. It's a tall building size. But this particular unit I'm showing you here is one of the good example of direct air capture unit in Switzerland by Climeworks, is that single unit is about my height. So this is the modular design, and instead of scale up and gaining from economics of scale, you're doing copy paste of a scale out. This does not benefit from scale up of economics of scale, but what we gain by is a faster learning curve. Each generation of direct air capture modular units been improving significantly so that you gain something else. But targets are very different as well. In the point source capture in chemical plants or power plants, we're trying to get 95 plus CO2 captured. And we can do that, no problem. But when you start from 400 ppm parts per million CO2 in air, it's very hard to get 95%. In fact, it's not going to be economical. So target is a little different. It's about 60% CO2 capture is the target. And there are other challenges compared to chemical plants. We need to have a low pressure drop because the amount of air we need to process to capture same amount of CO2 is huge, so that there's no way we can put enough energy to compress the air to get that pressure drop. So because of that, all the materials and systems we develop need to work with low pressure drop. We also have a lot of high oxygen concentration in air. That's why we can breathe 21% of oxygen. But oxygen also degrades this amine material, which loves to grab onto CO2, capture CO2. So we need to figure out how to keep them robust in high oxygen concentration. Another one is, as you can see in this photo, these systems will sit outside, and their reactor system includes the environment. And some days are rainy, some days are sunny, some days are cold, and some days are hot. How do we deal with all these fluctuating environmental reaction conditions make a huge challenge for engineers. So one of the technology we went back to and started thinking about with all these challenges was, I love the fact that our NOHMs material had almost zero vapor pressure, meaning that I can put cup of this material outside for days and days and months and years, it won't evaporate. Water would evaporate, but not our NOHMs material, although it's a liquid material. But it will do something. It will capture CO2. Not only it will capture CO2, it will capture all the dust because it's very sticky honey-like material. So what we tried to do was, can we create a lot of interfacial area and protect it from all the dust and other impurities, but capture CO2 effectively? So I start working with Yongju at Cornell University, my colleague whose expertise in electrospun membranes for fuel cell technology. I also collaborate with Michelle Kidder at Oak Ridge National Lab, who has developing many different unique polymeric system, which is diffusing gas, particularly carbon dioxide, very effectively. So our idea was putting these together and make the NOHMs goes to the core of the electrospun fibers and ultimately make the system like this, which kind of look like furnace filter, so that this will have very low pressure drop. And the key, another thing we were hoping to do is this PIM1, PIM2 polymers will be hydrophobic. Many of the materials loves to capture CO2, also loves water. So there's a lot of competition or we try to suppress the amount of water loading during the CO2 capture. So we made these fibers, as you can see here in our SEM image. And what we are hoping to do is to selectively reject the water while capturing CO2. And it worked really, really well. As you can see in this data, red one is on neat NOHMs without any encapsulation. The black data, which is much faster CO2 and higher CO2 capture capacity, is looking at electrospun like a furnace filter-like material. But, and then what we also checked was, would it selectively reject water? And definitely it did. So if you look at the top two, NOHMs material is really hydrophobic, as you can see in contact angle with this water. But PEI or TPA, the polymer without NOHMs, just untethered polymers, really did not have a good hydrophobicity. PEI did a little bit, but TPA especially migrate to the surface of these electrospun fibers and lost hydrophobicity. So we selected and concluded that NOHMs will be very good at electrospun system, and then that can be really used to capture CO2. So one last thing a little bit I want to talk about is that once you capture CO2, what can we do? If we care about climate change, we have to store. But remember, we talked about we can even do the circular carbon economy, which means that not only we capture CO2, we need to convert that CO2 to chemicals and fuels and materials. And perhaps if we kind of combine CO2 capture process and conversion, will minimize overall energy, process energy consumption to make the chemicals and materials. There are many different ways to do it, as I mentioned. One particular pathway I'm going to talk about today is electrochemical conversion. So using renewable energy electrons to convert the captured CO2 into chemicals and materials. There are many research groups, many research groups who worked on what is the better catalyst, what it should look like, what is catalyst morphology, how reactors should be designed. But one area, not as much research been happening, is electrolyte design. This is basically a medium where electrochemical reaction happens. What I thought was that traditional electrolyte is water-based, and the CO2 solubility in water is very low. So you can go to either get rid of all that electrolyte, go to gas diffusion electrode, or you can have electrolyte have a better solubility of CO2. So we went that route of making electrolyte better. So let's think about our NOHM system again, which captures CO2. Let's look at simply two solution phases. One on the left is the solution of NOHMs. On the right-hand side is polymers we actually made NOHMs with in the solution. And if you look at these two, what we care a lot about is conductivity as well as viscosity. So we want low viscosity and high conductivity to process CO2, convert CO2 into product. Since the only difference between these two fluid systems has a lot of particles running around on the left-hand side or the nanoscale, I thought that, well, if it performs as close to each other, maybe we'll be fine. So we went to the lab and tested this, and then what we found out was shown on the left-hand figure, NOHMs had higher conductivity and lower viscosity. And we were getting more confused. That's opposite to what we thought. So we keep looking at it, and we thought, well, it's consistently that way. Why? So we took this to Argonne National Lab. If you're not familiar with the USAX on the right-hand side, Q on the x-axis is inverse of the length scale. which means that higher the Q number means that smaller length scale material, like nanomaterials. So because these are nanoscale materials, you should have a lot of signals on the high Q range. But one thing you see is that low Q range, you start to see a lot of signals as well, which kind of hinting that you have some chunkier stuff, which you did not expect. So this is now we are envisioning. Our electrolyte based on NOHMs in naked eye is a clear fluid, but if you zoom in, it has agglomerates of a micron scale. If you zoom in even further, it has the tens to 100 nanometer scale aggregates. And because of that, there was very interesting transport pathways and channels, creating this to be more effective electrolyte. So now we had to just bubble CO2. Now you can load it up a lot of CO2. As you can see, more NOHMs, you have a higher CO2 loading in your electrolyte, which will be available to be converted to fuels or chemicals. And the conductivity, as you react, you see that you make carbamate and all these ionic species, you will even improve the conductivity of the system. Now we just need to put renewable energy, many IEEE the members will be making. And if you look at these systems, the first column is without NOHMs, it's just typical electrochemical system converting carbon dioxide to carbon monoxide. It's just a building block for or a lot of chemicals. Once you have that, we can make artificial jet fuel like sustainable aviation fuels or polymers and many more. The middle column is a chemisorb CO2. The last column is physisorb CO2. As you can see, the first column data and last column data look similar. Basically, this is showing that physisorb CO2 is an electrochemically active species. And we can definitely convert CO2 bound as carbamate if you heat it up the temperature to 60 to 80 degrees C. So as you can see, this is a selectivity data, but we were able to really capture CO2 effectively and deliver that CO2 to the surface of the electrocatalyst and convert it effectively to carbon monoxide and other intermediates for chemicals and fuels. Last few minutes, I want to talk about clean energy transition. I think this is one of the reasons we have this technology discussion, climate change technologies. Carbon management is part of the clean energy transition, and that's why we are working on it. But at the end of the day, even as a person who's working on carbon management for many years, we need to do it all. We need to do more solar, more wind, more everything, and more EVs. That is what clean energy transition is. But I want to ask you, is the clean energy transition really clean? I think that's the question we start asking a number of years ago within United States, for sure. And because of that, Department of Energy start to wonder where we're going to get even rare earth elements, these metals, to do that clean energy transition by having more solar, more wind fabricated and installed. It really requires a lot more resources. So now, beyond rare earth elements, REEs, we have a definition of energy relevant critical minerals. That includes all the metals, like minerals containing metals of rare earth, as well as lithium, nickel, cobalt, even copper. These are all needed orders of magnitude of these materials. So let me show you some of the photos I was kind of shocked with. I was wondering, I guess all of you have your cell phone with you today, and guess how much copper, let's think about copper in your cell phone. How much copper do we have? Maybe you guys know. I did not know, so I Googled it. It's about 16%, plus minus. If you look at your battery, it has a lot of nickel in it. So I was wondering, where did that come from? The left-hand side photo, this is one of the few man-made structures you can see from space. It's amazingly large. This is copper mine in Utah. And on right-hand side, this is a mine, which is a mine tailing actually. After you mine all the nickel, this is a waste sitting there in Vermont. So when you call something copper ore or nickel ore, instead of calling them rock, only difference is they're solid mineral, which has high enough value, economic value. So if this copper mine is saying this is copper ore, it should have enough copper in it. So I was wondering how much copper. And when I checked last year, it was 0.44%. It's shockingly small, right? And nickel in nickel mine tailing is, or nickel ore is the 0.2%. So this tells you in order for us to do clean energy transition, we literally move mountains every day. So let me ask you, do we love mining? Well, I think we had that conversation decades ago, right? And there are huge environmental concerns. I'm not saying we cannot do clean energy transition, should not mine these materials, but now we know the challenge. We need to think about how to recover these metals for clean energy future by doing sustainable mining. And that also links to how to store carbon. So there's a lot of synergy between carbon negative mining and clean energy transition. So going back to where these mining can happen, and in United States particularly, I'm working with Rio Tinto in Tamarack, Minnesota. And it was really interesting when I went to visit this Tamarack, Minnesota, which has a lot big nickel and other mines and rare earth as well. There was Tesla driving around and had their bumper sticker was they have a carbon neutral nickel in Tesla. So I thought it was really intrigued because they're going to get nickel from this mine site, but at the same time, they're going to capture and store carbon dioxide. Very interesting synergy between two technologies. The challenge becomes because you're trying to get nickel at the same time store carbon means that you're going to have a system of complex ionic solution with a really high concentration of, for example, calcium and magnesium and very low concentration of nickel and even cerium and more rare earth material. The challenge becomes a separation, how to get to this low concentration metal, keeping the calcium and magnesium in solution for downstream carbon sequestration. So we looked at the biology does really well. And in fact, biology knows how to create multiple binding sites with the right cavity size just for target molecule or target metal like cerium. So we start designing structure ligand system by putting scaffold with the ligands in right distance from each other to create the cavity. An example was we wanted to capture cerium in the presence of a high concentration of calcium and magnesium and other ions. And I'm not going to bore you with all the different binding energies, but data shows that cerium, first one is a cerium only, and then the other three columns showing that cerium against sodium, calcium, and magnesium, and it always performed really well. It was able to go after cerium and only bind to cerium while leaving the sodium, calcium, and magnesium in the solution. This is our DFT calculation showing how and why. And first column shows that cerium is bound to all 7 binding sites just snug because the size of cavity, distance from each other, all these binding sites was just right. But calcium and magnesium second and third data shows that they kind of bounce in and out because it cannot be perfectly bound to all the binding sites. So now we need to think about all the separation technology is catch and release and catch and release. Remember that? So we're going to do release again. So catch, this capturing metal is a pH around 8 or beyond. That's the where metal binding happens. And as you lower the pH of the solution of system, about pH 4, you start to release that CO2, the metal into the solution phase again. So you can do catch and release. In order to that cyclic, now you need to do pH swing. And if we are doing this with acid and base, it will cost, again, environment because all this chemical footprint and environmental footprint. So in order to do green chemistry, we are thinking about how to do this swing without using harsh chemicals. And what we were able to, what we hypothesized was maybe after we capture the metal we want, energy relevant metal, we can bubble CO2 and acidify the solution, lowering the pH. And then once we release that metal, we can increase the pH again by just bubbling air and degas the carbon dioxide, which is acidic gas. So interesting way, we're using the material CO2 we've been talking about again as a green chemistry here. And this is our data. Once you load a lot of cerium in the system, the red column is showing that by simply adding nitric acid, strong nitric acid to lower pH to 1, you get most of the cerium out. If you use at the pH 3, you only get 35% out. But we simply bubble CO2, which is not toxic, not harsh chemical, very simply bubbling CO2. We got even more the metal out, and cerium was over 94% recovered. We were really pleasantly surprised. And when we looked at the system, if you look here at the bottom right, the system looks different because the bottom section where cerium was coming out was very cloudy. What we saw was that we were actually making cerium carbonate as a product. So because of the precipitation, we were pulling more of cerium out of the oily phase. This was really interesting reactive separation we discovered so that we can actually have green chemistry of recovering these metals at the same time, leaving the calcium and magnesium in solution phase for carbon sequestration. So a big question I want to ask you to end with, is this is this nickel in Tesla going to be carbon neutral? Well, it's a big question, right? Let me ask you, I don't know, it depends. The question I also maybe ask is that we can make jet fuel, we do now from crude oil, or we can make sustainable aviation fuel, jet fuel from CO2 captured from environment and hydrogen, which is carbon-free, and renewable energy. Which jet fuel is better for the environment? Unfortunately, this answer is not that straightforward. We need to have a robust life cycle analysis to really understand and increase the system boundary of how we evaluate technologies to get there. So I want to conclude that it's a really interesting time, in my opinion, in carbon management, carbon capture, utilization, and storage community. This is almost the first time last 5 years or so, there's a huge synergy between renewable energy community and research field and CCUS research field start working with each other. I think a significant amount of, or huge amount of renewable energy is really critical for carbon management. And with electrification, we talked about a little bit at the end of the last session, as well as reactive separation based on electrons, will be key for creating the sustainable chemical industry for the future. And hopefully we'll be able to create the new pathways to existing chemicals, but perhaps even new pathways to new chemicals, while keeping all these technology development. The system boundary should include the earth and environmental systems and humans within system boundary. Here are my funding agencies. I want to end with showing the one report just published. I was part of this National Academy's report on carbon utilization infrastructure, markets, and research and development. And this report, if you look here, you will see all the products you can make using renewable energy and carbon. And hopefully this will show you more background information on where we are going, what we can do together. Thank you.
Alissa, thank you very much for an interesting talk. Ravinder was called away. That's one feature of an online conference. So I would like people to put some questions into the chat. It looks like there's one from Saiban. Is there benchmarking comparison of carbon capture rate of various technology versus bio-based approaches such as vegetation and seaweed?
Mm-hmm. So there's no benchmark data yet. Even looking at the CO2 capture materials, we don't have good benchmarking. And that's what people have been talking about in our field, that if you look at solar energy, if you go to National Renewable Energy Lab, they actually has this map of all the solar cells, right, how they perform. We don't have something like that because we don't have a place to test same material together. They're trying to do that. There's a National Carbon Capture Center, try to ask, like all the performers, researchers can go to their site and kind of plug in their technology. It's not only about the materials, it's the systems as well. Unfortunately, we don't have that yet. We are trying to get there. We always have a target though. DOE always comes up with this is the target amount of energy and all that, and everybody's moving towards that. I think this is the time for us to really think about it, especially direct air capture. There's so many parameters we need to tune. I think it'll be hard, but we should have a tough conversation on it. I'm going to compare direct air capture, which is the hardest way of capturing CO2 because low concentration in air, compared to planting trees, vegetation. Per square feet, we can capture more CO2 within given time because we're chemically capturing it. We're even moving air using energy. We are putting more energy in. That's why we can do faster CO2 capture. Plants do less, but sometimes people ask, oh, in that case, we should do only direct air capture. I don't agree. The reason is that planting tree does more than capturing carbon. There's so much more. So there should not be only one solution to this. We should plant as many trees as possible. At the same time, certain areas we can definitely do direct air capture. And there's so much co-benefits of planting trees. So, or having more reforestation and all that, I don't think we want to just compare apple to orange of how much carbon can be captured per square feet of space. That's a little different question, in my opinion. There's very interesting discussion. I was visiting South Korea with director of ARPA-E, Evelyn Wang, because she was discussing seaweed energy. That was really interesting. What they were saying was, inland, we don't want to change the land use as much because it also does a lot on carbon cycle and how CO2 is emitted into the atmosphere. So what they wanted to look into is ocean-based technologies in addition to terrestrial. So now they're looking at how to grow and cultivate these seaweeds or marine biomass grows really fast rate and what to do the end of their growth cycle. And that's interesting. And they were in South Korea because apparently South Korea is excellent at cultivating seaweed. So maybe this is another technology area we'll consider looking at the biological pathways.
Okay, there have been a number of compliments for your
back
talk.
in 2016, helped him raise a lot of money, spent 9 months on the campaign providing media advocacy, and then worked on that transition for the 12 weeks of the transition as an executive committee person. So it wasn't just 11 days in the White House.
Dave, can you
I'm trying to find him.
To many people that work with him, if not all the people that work with him.
Okay.
Sorry about that.
Okay, there have been a number of compliments for your talk. I have one question while other people think of other things to say. Can you talk about all the different colors of hydrogen? I only thought there were 2 colors.
Yeah, that's interesting, right? It used to be only 2 colors. Which one do you know? So,
Green and black.
okay, so black is the cheapest carbon hydrogen you can make. That's from coal. You can gasify coal and do water gas shift reaction. Then all the energy in coal will make hydrogen. You can definitely do that. That's cheapest. Gray hydrogen is converting natural gas into hydrogen. So that's less per energy, the carbon intensity. So hydrogen from natural gas is gray, not black. Green is when you use renewable energy, electricity, to split water into oxygen and hydrogen. That's green, really carbon free, as long as you used the green energy, right? Renewable energy. The blue is making gray hydrogen, which is a methane to hydrogen, and the carbon associated with the hydrogen, we are capturing and sequestering, then it becomes blue. Let's think about, the pink one is using energy from nuclear plant to split the water into making hydrogen. That's called pink. Because we have debate over, is nuclear energy truly carbon free? Well, it's not problem free, but there's a lot of debate over this. So that's a pink color. It's not the same as green, which is solar and wind and all that. Other colors include, for example, let's see, the white hydrogen. There was a lot of debate over geologic hydrogen. So in the Earth system, there's pockets of hydrogen made by during the weathering of rocks, and they haven't really submerged came out of into the atmosphere yet. There are pockets of these. These are natural hydrogen. They call it white hydrogen. The orange hydrogen is new because now in geological formations with the potential to make geological hydrogen, but they haven't made it, they actually are thinking about activating the geological formation to make hydrogen in situ and extract them out. That's orange hydrogen. So there are continuation of these. I'm sure there will be a new color for hydrogen made out of the seaweed, right? So, but just color coordination just means that what does it mean to carbon footprint of that particular hydrogen? Kind of interesting.
Okay, thank you. There's a question, can you give us any information about comparative damage to geological features for different kinds of mining and drilling for fossil fuels? Before you answer that, I'll point out one thing, that the volume of lithium mined compared to the volume of coal is insignificant. So remember that coal has a huge impact on the environment. But anyway, the question again is, can you give us any information about comparative damage to geological features for different kinds of mining and drilling for fossil fuels?
So I'm not a mining engineer, so I cannot really tell you the damage, but let's talk about what are the concerns we have about mining. It can be open pit mine, just a mining from the top, or you can go into the seam so that you do below the ground. Or these days, the lithium are mined from brine a lot of times, which means that under the geological formation, there will be pockets of brine. And then in Chile, for example, there's a huge brine mine they found, and they basically pump this brine out of the reservoir, and then you have to evaporate the water to get the lithium out. So what they're doing is they just make ponds after pond after pond, and then just using sunlight to evaporate, like almost making your salt, right, from the seawater. So they actually do that. But that particular area hasn't rained for 100 years. By doing all these, you will change quite a bit of ecosystems and there'll be a huge environmental challenges. I'm not saying we should not do it, but we should be really aware from the day one what consequences we could have. All these mining industries use a lot of the energy, so they have a lot of gaseous emissions, but solid, a lot, as you can see here, as I showed, the amount of nickel, amount of copper, amount of lithium in these resources are very low concentration. You leave behind huge amount of solid fine dust, which could be environmentally damaging, acid mine, which we have to deal with. So environment and water we require to do all these, and chemicals are huge. So regardless whether we're doing huge coal mine versus the smaller lithium mine, mining is mining. It does have environmental impact. So I think knowing that is a good thing, because as a chemical engineer, when we built the first or designed the first coal-fired power plant, if somebody told us, the engineers, that you have climate change issue with all the CO2 you emit, I'm sure we did something about it. I think we are at that junction, which is a good thing. Let's have honest discussion on what could be all these environmental consequences. And even if it costs a lot more, maybe we should take care of it from the day one. Then we can really truly have clean energy transition.
Okay, there's another question that starts off, are there any technology for CCS from air with cost efficient for industries? A different wording is there any open research of CCS to study and implement it in real life?
Yes, so we actually have, as I shown you, carbon capture has been demonstrated the biggest scale at Petronova site in Houston. So you can do large scale and deployment. Interestingly, direct air capture has been deployed faster because it's a modular system. So industries can go in quicker. And we talked about some of the companies actually are making construction materials or even fuels. And then Charles, I think you like the whiskey part of it, right? There are many products they are actually making today. But is it going to be enough to decarbonize the entire economy? No, not there yet. To be honest, a lot of people ask me, when is the day we're going to have a circular carbon economy? Well, we have to continue to improve our technology, catalysts, reactor systems, and all that, as well as lower the price and energy intensity of this process. But I hinge upon renewable energy sector. You really, in order to have a net zero economy, I'm sure you need to install at least 3-4 times more of capacity of renewable energy. You need to fully decarbonize the power sector first. We need to do that so we don't burn coal or natural gas anymore. At the same time, you need to additionally build, because now instead of using natural gas or petroleum, we will use renewable energy to create the whole chemical industry. So that additional electrification will require a huge amount of installation. So even if we have best technology tomorrow, which we're not gonna, we will take a few more years, if renewable energy installation, that infrastructure is not there when we get there, will be limited. So I think this is very interesting discussion we can have between IEEE and rest of the chemical researchers and technology developers, how to look at where renewable energy is, where we're going to get the even grid, and where we can put carbon capture and conversion systems to be even positioned, linking all these through interesting infrastructure development. And I think this is the right time to have that discussion.
Okay. That's very, very interesting and good. I don't really see any other questions. So I think now's the time to thank you for a very interesting talk. The chemistry side of this is out of my wheelhouse, so it was very interesting seeing it. Thank you very much for an excellent talk.
Thank you. It was nice talking to you.